Back to MLBs. Actually more now.
No, it's
You know, the underneath.
might not know. Can you close that?
Okay, yeah, if you have any questions, please ask, because a lot of this is not. Going. If you have any questions, I think they also saw recently that pretty high level graduate math courses, so I can, it's like not, it's not very trivial. And I also don't understand some of the things. Please help me, and also please ask if you have questions. It's not. I also have one question.
It's a discussion everyone.
Yeah, exactly. Well, I'm just saying, like, you know, because I understand it may feel like, oh, maybe I should know these things, but I don't think it. All right. So so I'll just jump straight in. But like what they want to do is use state space models, which are very common in any type of engineering for dynamics to model time series. So be that like sequence to sequence models, like transformers are doing now with like word prediction, or be that forecasting, or understanding the dynamics or whatever. They want to use continuous state space models, and continuous state space models, this you may have seen before, but they're very general systems. They're linear systems where you have the derivative x dot, and you have an A matrix that multiplies the previous state, and then you have B, which parameterizes the input, and then you have Y, which is like a function of the state. And so you can generally assume that E is going to be 0. It doesn't really matter that much. That's also what most people say in these models. But so the main interesting thing is that if you look at the figure, is that you essentially have, you can look at it in this block diagram. You have U, and somehow you map that to Y, and you can think of it as like going through a lane space X. That's the way you can think about these things. That's also how they think about them, and how they're going to talk about making them more efficient.
So interaction is okay.
Yeah.
So if you rotate the figure 90 degrees, it's an RNN.
Okay.
Like usual representation of RNN, how they draw it.
Yeah. That's where I was going. So yeah, I'm not going to go too deep into this, but because this was like 3 papers that they essentially published. But one thing they've shown is that if you have a specific type of A matrix, you can actually remember all of the previous inputs. So like x dot, you can think of x dot as containing information about U, right? Because you get AX plus BU. So x dot contains information about U. And each time step, you're going to forget something about U because of long range dependencies. That's the issue with a lot of RNNs and stuff like that. But if you have a specific type of matrix, like this type of matrix, so the A matrix that you see on the screen here, they call it a hippo matrix because people have very good memory. Actually, remember, yeah.
It's got to also stand for something.
I haven't looked at the other paper. Something like high polynomial order.
There's elements that have very good.
But I think I mean, they have a literal photo of the Hable in the brain, so I think it's pretty hard to do it. But also, but yeah, they show that like if you have this type of matrix, you can model huge long-term things. And one of the things to say, for example, is that when you do like a normal ODE, or if you do an RNN, oftentimes you're solving an equation with an exponential.
What is this type of matrix? That's what I was getting at.
Yes.
All I can see is it's lower
It's
triangular.
for a polynomial,
Is it?
something like that. Or orthogonal polynomials.
But it's a DAG. Okay. It's like the first node doesn't get any input on
So
itself.
it's an adjacency matrix
Yeah,
for
yeah.
a DAG. Okay.
And then it's like, yeah, then I think so. I don't.
But it is based on orthogonal polynomials.
Topological sorting.
Right.
It's not like like the same if you kind of use Fourier like this, you like
It is related to VA.
put on different values, like frequencies.
Yeah, it is related to VA, but that's also why it's polynomial.
Maybe it's like the point of smart is kind of you remember in steps, and like these models called like invertible layer on box. what they do, like they have some specific like operation that kind of allows you to turn up the non-linear distribution.
Yeah, but I think this one, you should think of this as non-linear distribution.
No, I don't think it's just saying that like it's kind of related, like you want to kind of remember. Like, you want kind of model kind of future steps, but like you also want to remember previous steps. And so you need kind of both information on different kind of preferences.
This is specifically for all previous steps, and so I didn't want to go into this too deeply, but the way they think about it is like, if you can model all previous steps using polynomial approximation in a lower dimensional space, you can find that approximation. And this is the bit, like, if you then do some linear algebra and you get this matrix, or you first map it to a polynomial basis that is like lower dimensional, and then if you use linear algebra, you can get this matrix back specifically for the stage of the problem. So what they're trying to do is they're trying to model all the previous time steps as an approximate polynomial,
Yeah.
and then they use that essentially to like, yeah. Then it's like, yeah, it's a couple papers, so I don't want to, you know, I didn't want to like really go deep into like how this specifically works, but you should think of it as like, okay, well, what if you just, let's say we have at a point T, what if we could just model all the previous time steps as like some sort of polynomial, like we just fit a polynomial to that with a certain order, and that's what we use like remembering. That's the way you should think of it.
Okay.
That makes sense. So we have like weights for the polynomial that we can use to understand previous time steps.
It's like in pieces like presentations.
Yeah, yeah, and so yay is, so they say like they use polynomials, because that's a good way of doing it, but they also say this is a general method, you can use it for, well, yeah, you could do any type of decomposition.
Yeah, and I just want to kind of connect this also like this investment level things. So also do kind of some fix with how you handle like transformation. So it's kind of the same thing. But it's just like it.
Sure, yeah. And I think the reason why it's important to think of it like this, where you have an input U that maps through X to output Y, is that if you want to keep information in X about you, you need this special type of A matrix. Essentially, that's the way you can do it. Like, and think about X as like a memory block. If you don't want the information to dissipate, you need these special types of A matrices. Otherwise, in the next step, when you update X with X dot, you're going to lose information about you that you want to take.
But you're gonna use it no matter what, because your A is not infinite, so you're keeping up to certain frequencies.
So that's also what they say, it's like a subspace, right? Because you can't do it in the polynomial order. But they explicitly, like, the point is that like every time step is as important as every other time step. That's what they try to do. So it's like they say it's like a uniform measure onto previous time step space. Because with RNNs and with normal ODEs, when you solve it, you do an exponential, like you solve an exponential equation, and you get e to the power minus tx. And
There's okay, but not with OSTM, like you can choose to remember.
they actually show that there's a k. So that's
But you can choose to hold one value or indefinitely, never forget.
well, these models don't have issues with grading, forgetting, and LCMs do, right?
But those models, you said every time step is equally important or equally unimportant. They have the same huge error, for example, on each time step. Like, I wonder.
The previous time step, right? So when you think of an LCM, realistically, you could learn maybe to like remember everything.
Not everything, not everything.
That's not really what happens, right? You generally, the most recent points are the most important points for how you predict the next point, right? There's some inductive bias on like,
Yeah.
I want to use most of the previous, but so in this one, the inductive bias is we just use everything, right? All as much as we can from the previous time steps.
So what's special about A? It's really, really, really big.
No, it's this type of like this type of.
It just gives you the basis for it.
But it's basically like increasing capacity. Like you have more constellation. Like for example, like the more rows you have, like the more things you can memorize.
I think so, or at least the better your approximation.
Well, it's kind of like the higher frequencies you add to your approximation of the time series.
If your time series is perfectly quadratic, you can model it in two-dimensional
Mhm.
basis, but it depends on the wiggliness of that.
D and C are learned.
A is not learned. Okay, so it's.
Yeah, so A kind of,
Okay.
and one kind of pieces like
Yeah.
that. You know,
Yeah, so A implicitly remembers everything, and B and C are essentially the matrices you learn so that you map into the correct namespace.
okay, you have an info paper.
Is there any issue with the polynomial not being valid?
I don't know.
Okay.
But you kind of successfully updating the values of those coefficients. That's it. You choose how many coefficients you have by the size of A,
Yeah,
and X is the coefficient, values of those coefficients.
Yeah.
Updated,
Right.
just to.
but it's done in a way where you explicitly don't forget, you average it constantly, right? You don't do like, oh, the first point is not as important as the current point. Right?
Yeah, you're trying to feed the entire thing.
Yeah, you're trying to essentially like slowly average it together instead of, like doing exponential stuff, like a, what's it called, weighted average thing, you kind of say. Previous points are not as important.
I think I might be getting hung up in my mind on this polynomial approximation idea, but I mean,
Well, this is why.
it's just like a reason that people make polynomial approximations for activation.
This paper is pretty hard. This is
Yeah.
So this is what they say. They say like, see, this is the.
No, but HIPAA doesn't come from them. It's a standard term, like they cite in this paper somewhere in the beginning, they cited somebody else's work. It's already, somebody else gave that name and.
I know, it's like. They also make the connection. Yeah, so this is what they kind of do. Is like. You project like a polynomial onto every previous time step where U is the uniform measure. So every time step then for the other. And then what they do, this is the. It's a little hard to explain. I've tried to like read it for the video, but. Yeah, so they say like there's an optimal projection at every time step for all the previous time steps. And so they say weighing the past, but in this case, it's just a uniform distribution. UT. For an appropriately chosen basis, the corresponding coefficient CP represent a compression of the history event satisfying linear dynamics. And so then they discretize it again to get it back into the form they want to solve the second equation. And then they don't even talk about it explicitly, like the matrix here in this paper, because the info is more general. They do, by the way, this is also their paper. I think they actually cite themselves. But so they just show here that for any, that you could do this for everything. And then their next paper is, well, what if we do this for linear state space layers? And then they talk about how you would get this type of matrix specifically for linear state space models. I think that's like in the appendix of this paper.
I may have read the anonymous version of it, so that's why I didn't know who they cite.
Yeah, I think they cite themselves, so it is still, but yeah. Yeah, to go into this very deeply, because this one is just a really like mathematical. It's just like, oh, what if you have a Legendre and metric?
Yeah.
So it's like very go to the.
So did they actually look at the gradients? So if it remembers, then the gradients, there's me no organic gradient. So did they actually look at the gradients?
Well, so let me just go over how they do it, because there's also way more things that they do. Do you mind if we keep going? Just imagine that it works. I mean, it's kind
No,
of.
but can you summarize just the main idea is that they kind of retake once a new point arrives, they repeat effectively, they repeat the polynomial of fixed degree to the entire previous time series. So that's it's the best thing. Effectively, they're doing it efficiently, not like that. But
Efficiently, and they're doing it in a way where you just have one matrix that the like it does this for you automatically without having to explicitly say.
Okay. Do you mean literally fit?
so that they are so the polynomial.
So normally, if you did the projection, right, you have just like a matrix that like a basis of polynomials. So what they do is some linear algebra tricks where what they would do normally is like, let's say the time series, and then you do a projection of that time series with those into like the polynomial subspace, right? And then you get like weights for the polynomials, right? And then they do some tricks to make sure that those weights essentially constantly get updated for the previous time steps without like this ability.
So the A matrix is essentially.
No. The A matrix makes sure that X retains like the information for these like basic weights. Like, that's the way I kind of was thinking about it.
Okay. Oh. Yeah. So A is just a function of these bases. So
Well, I projected so that
it's polynomial, it's just some weight value defined.
well, X dot would be the weight.
Like generalization of sleep financial.
Also, yeah, that's also official. Yeah, so we're gonna go into that also more. This is what the hippo matrix looks like, just like as a general form. So they don't learn this, right? But for example, what they do show is that if you do sequential MS benchmark, just using this matrix, you get like from 60 to 90%. So it's pretty cool. I mean, I think it's a cool trick to like essentially make things more stable.
But it works only like when everything is equally important. If there is only like one time flash of important stuff, so it wouldn't.
So they talk about that because when you think about what C and D do, they are sort of like feature extractors. So if you remember everything, right, you can still extract a feature if there was something very important happening.
Not really. If it's not, it depends on the frequency, like on the order of polynomial needed to capture a feature. It would be totally smooth, for example.
Sure. Well, I mean, they show that it's better than everything that exists so far. So I guess like
So our benchmarks don't have
you
that.
really, yeah, at least the benchmarks don't have it. Okay, well, so we can think of this as a different way. I mean, it kind of already was written this way, but like it's like a ordinary differential equation. And so in this case, f of t on the x of t is just, in our case, it's just ax plus bu, right? And so we can write this, if you want to think about every time step, instead of the derivative, we can think of it as like current time is the initial condition, x to t0, plus the integral, but like the integral from t0 to t over this function f. So that would be like the way you, does it make sense for everyone? I mean, if you think of it like integrating over the derivative, that's what they're doing.
Euler's method.
No, this is not really like this is literally equivalent, right? This is just the
Well,
normal.
because the integral is not the net.
But then after that, yes, you can do Euler's method too. But yeah, so they talk about like, okay, well, we don't want to do an approximation, and then you get I plus 1 because now you don't get like points like continuously, but you get discrete points. And then if you want to discretize it, have like discrete points like t I plus 1, you get x ti plus this interval between ti plus 1. For people that have worked with neural ODEs or ODEs, they just normally solve by like numerical solvers. So there's like a million different ones. You know, there's like go-free, there's Euler, forward, Euler backward, bilinear.
Oh, but Euler is unstable, so I wonder.
Well, they don't use Euler, but I'm just trying to give people.
Okay.
Yeah, so the Euler's forward method would look like this, for example, right? You would get xt plus 1 equals xt plus t.
Actually, that's a thing. That's what we're on most.
Yeah. But what they say is like, okay, well, we use the bilinear general form, and the bilinear general form, if you set at alpha, so that's this one, this equation here below. If you set alpha to 0, it's the same as Euler forward, because if you set 0, you get I, like the inverse of I, and then you get times I plus A, so then you get I plus A, and then at the other side you get like minus I. So
It's like one form, right?
I have alpha is equal to 0.
He's not doing fine. He's sick. Sorry. Missing a person. I was like,
Okay. Anyways, yeah, so 0 would be, I think, either Euler's forward method or backward method, and what they use is path, because that's like a very stable way of doing it. It looks very impressive when it's in your own. And so what you get then is this. So if you discretize, so initially we had this equation, right? Like AX equals BU, CX equals DU, and we had this is a continuous time ODE. And so we discretize it, and then we end up with this. So we kind of get xk equals a of xk minus 1 plus b times uk by a c times a. So this is nice because now we can kind of work with it, and this is more similar already to something like a R.
Can you pose, a bar, so A is that polynomial heap on my matrix, and a bar we can do that from the. And so then we'll go to normal space model from the differential equation. And we have the guarantees that it's still one.
Yeah.
I like to see bars up there. Easy number.
Yes.
The C bars is equal to C.
Yeah, I guess they just do it because it's better to just explicitly. But yeah, like you can see here that they use alpha equals half because you get this like half.
I guess it's not also like from choice of the new system. Makes it say because much more complicated stuff.
Yeah. They just say like bilinear is one of the most simple but stable ways of doing this. And if you do very complex numerical solvers, this would be extremely annoying to solve because you would get like this already. If you think about the base multiplication that you have to do for every time step now, it's like a lot, right? You have to do. You can do it in a smart way because you have like a diagonal matrix, but still, it's like a lot of computation. All right. So yeah, so this is for sure we talked about just now. So one of the results I actually showed in the previous paper, not this one, the previous paper, but I thought it was interesting because I knew Noah was here.
Yeah, I'm glad Noah is here.
Is that they essentially say like these space models are gated RNNs. Yeah, so I'll just go through this. So they say like if you have a gated recurrence like you have in RNNs, that's like the XD equals 1 minus the sigmoid of Z, etc. It is an arbitrary expression can be viewed as the general bilinear transformation, which is the one that I just showed, where alpha equals 1, which is the backwards Euler interpretation of the 1D linearly. So remember this discretization that I just showed. If you put alpha to 1, you essentially get a gated recurring level. So
And the gate comes from where, like the decision, the sigmoid, where it is what? So sigmoid of Z, what is how it relates to your general equation where with alpha not set to 1?
I think the way it relates is that when you think about like, so it says it below, right? If you solve this equation, like if you solve a linear ODE, you get this exponential function, right? Which is the same as this 1 minus sigmoid. If you go for like the solution to a long term. And that's the same for their linear state space equation. Like you would get e to the power a, right? Where if you set a to minus 1, you get the same thing as the part. That's the
Yeah, that's interesting.
So this is probably a better time to interject. LSTMs are just the gated RNN.
right.
But the proof for them having vanishing gradients is actually based on the eigenvalues of the forget matrix.
Oh yeah.
They show there's a proof that if the max eigenvalue of your forget matrix is less than 1,
Yeah.
you will get vanishing gradient. And I think that's interesting because they're doing all this stuff to find A that provably has a max eigenvalue greater than 1. Because a polynomial matrix is going to have a max eigenvalue higher than 1.
Right.
And so I mean I have no idea if they talk about that as a proof or if they even look at the gradients. But it's interesting, and I actually trust them at face value.
Yeah, because that's the thing, right? Yeah, so that's a good point to bring up because if you think about e to the power, yeah, it's like one of those things you learn maybe or you haven't learned, but like if you have a solution to linear ODEs, it can be the form e to the power AT, where if you take the eigenvalues of A and they're larger than 1, that means that it's not damping.
When it's exploding, it has to be, the largest has to be 1 for
Oh,
stable.
exactly. So it needs to be 1 exactly for stable system. If it's smaller than 1, it's damping. It's a very much damping effect. And so, yes.
But you don't want either. You don't want damping, you don't want exploding.
No, no,
It actually might be.
It's one complex, it's like, oh,
Right, so. I think they should call LNM as like special case of a system, but not a system.
yeah, I should have maybe not used this way, like, yeah, it is.
This is a good conceptualization.
No, that's good, but I think it should.
No,
be-
my title was, yeah.
RNN abbreviated as system.
Yeah,
Yeah,
RNN for-
a special case.
yeah, I should have.
Because the analysis regional is also common thing in stability control.
Well, yeah, it is a very special case because if you think about it, it's just when A is -1.
And then probably like
But potentially RNNs are more general. It's that requires a specific form of transition matrix. RNNs can have any form, so I don't know who is the special case.
No.
it's still all like systems, right?
RNNs are based on like a linear ODE that you just discretize and then.
Oh, yeah, but that, so RNNs are discrete, yeah.
Yeah, and they specifically use backward Euler to solve the discretization, right? It's a very special case of an ODE. That's why they did neural ODE. They said, why are we doing this?
Because LLM has like special form of function, right?
Is this NHW as
No, that's not what we're talking about. It's just that picture in the beginning.
I agree with you that you can learn, the learnability is nice, right? I'm just saying, like, if you think of it from an ODE perspective, an RNN is a very specific way.
No, it's a
to solve it.
discrete system.
And specifically backward Euler, right? That's also very important because you predict the next time step using dx, but you learn those things, right? Like it's a little bit more complicated than just saying anything, but like, yeah,
Okay, anyways.
from the perspective of if you only study these. Okay, well, the next thing is that's really cool is that they show this in one of their, there's like 3 or 4 pages, is that you can actually model these state space models as a convolution. And this is where it gets harder to.
But that's the interesting part. Yeah.
That's the interesting part, right? Because if you want to solve this, right, what they say essentially is that if you have this recurrence relationship, it's like horrible, right? Because it's like in flow and you have the same problem sometimes with RNNs, and that's why transformers have become so big. What if you could just solve it as a convolution? And so just think about like what this looks like, right? So if we have our step 0, the first one will be the I'll just call it C. So x0 equals b 0 and then y0 equals c. Next step, next one. We have the previous time step plus this new b r u1 and for y1 the same thing. You know, we can keep doing this, right? And we get these new terms that are like of the form a squared b u0 and Brad may already start to recognize the Krylov subspace. But this type of matrix, where if you look at yk, it has this form of like c a to the power k. So this a to the power k is like a special form, and we generally call that like a Krylov subspace, which is used for finding the largest eigenvalue. There's a lot of numerical linear algebra ideas around this Krylov subspace. But it's essentially a space that's spanned by this A matrix to a certain power, where the power would be R, and that's the size of the space. So like A, yeah, so if you does that make sense? Like if you look at YK with this type of like A to the power K form, that the Krylov subspace that also has that form spans this like C A to the power K B U0 space essentially. Oh, sorry, yeah, not the U0, but the C.
So they simply kind of unroll the equation.
Yeah.
And roll down the.
Yeah.
And A is the only matrix that is repeated.
Yeah, exactly. So what they say is like that is very, very extremely, that takes a lot of like compute. Right, this A matrix, I mean, although it's lower triangular, it still takes a lot of computation to do like this. For every time step, you have to multiply by A, and you have to multiply by.
The same cubic complexity, yeah.
So, okay. If nobody has questions, I'll.
No, wait,
Yeah.
I have questions. I don't have questions yet, but so the first one is the unrolling.
Yeah.
And then how did you jump to the kernel? What is the kernel? Because the kernel now depends on K, right? Oh, okay, so you're writing the kernel and the parameter is where and time and it's located.
Yep.
And then you.
Yeah, and you would have to multiply by A.
But like, do you recompute the kernel because you still multiply by you still raise A to the power of K, so you have the kernel.
Right. So you can think of it. So it is like a little bit of like obfuscating like the way they write it down. But I think they just want you to think of like, if we had the pre-computed one, it would be convolution with U.
Mhm.
The way they do it would be that at each time step you also have to multiply by A, which makes it so expensive, right? Like this, at each time step you have to multiply by A to get the actual A to the power K. The way they actually solve it later on is using 3 different FTs. Because you don't have to use, right, if it's a convolution, you can just do FT of these matrices.
Well, the convolution is a product in the frequency space, but still you have to compute what you're producting with.
Yeah, so
you
I
have
think
to raise
what
the K power.
So I think what they do is you can also see this as like, they don't talk about this very specifically, but I think what they do, they think of it as like a convolution with A and U. And then if you do that if you take the we out of that, then you can do that very efficiently.
I'm interested in the current actual details, but yeah, I get the idea with the pre-computation. If you can, A is known for all of the time series, so you kind of can pre-compute all of the powers, but then it's kind of inefficient anyways, memory-wise, etc.
The thing is that what they essentially say is like this is common knowledge for LTI systems. That's a little bit how they talk about it in the paper. This is like the previous paper, which also didn't say it. I don't think it's in the full paper. What they say though is the way the computer just uses 3 different FPs.
So, but can you, or should I talk about why it is interesting, why it is important for people who like missed the evolution of STM and became sure. Like transformers? Because STMs were super powerful and they still are, but the problem is training and using them. You have to know the previous result in order to compute the next result. And for any kind of time series, you have to go sequentially. With CNN, one can do CNN, even though they're talking about Fourier and all of that stuff, but you can just simply in parallel apply and the future use apply all the kernels in parallel, multiply everything. So this allows us to compute it. That's what's funny because this is a state-space model, and in state-space model there is that recursive or recurrent dependence on the previous step, and yet you can compute it in parallel and just by multiplying because their A is already
because of the LTI, right? Specifically, I think that's like one of the because they use LTIs for filtering too. Yeah, so that's the thing. It's like there's a lot of like previous like linear algebra literature that goes into this kind of stuff.
So what exactly does time invariance mean? They assume like stationarity or
well, they B, A, and C don't change, right? That's
but the same about the STM and other. So it's
but it's not linear. That's the thing.
It is not linear.
the same things in application change.
No, you're learning it, but it's not, it's the
Yeah,
same.
you learn it, but it's the same over time, right?
But in
A is not learning, yeah. And
You
it's
also
also,
can see there's also
it's
over
over
time,
so changing is statements.
but it's time and variable.
X and U change.
Yeah, over time.
but then
A, C, and D don't.
Like if you're learned LTM, you're not changing the double picture,
but it's not.
but it's over time.
But X is like kind of statement.
Yeah, but not really because an RNN is non-linear.
Yeah.
Right, so that's like the difference, that they can use these types of tricks because they're using LTSs. And just for people's, like, you may think like, oh, it's completely linear, but you can learn U to be a non-linear transformation into the space, right? Like, U doesn't have to be a linear thing. You can be learned, like you can.
Well, it's kind of like, yeah,
It could be an embedding, right? Like you could be a complex embedding that you learn, and also Y going from CX E, you can go do complex convolution, for example, back into a large dimensional space, right? So if you couple this with like an autoencoder, you can be in a very complex space, like a very complex geometric space, lower dimensional, but the system itself is linear, and that's like the most important part.
I think it just makes an assumption is like the visitation space should be linear separate. Or it just says that locally we can do this linear. So
Right, no, exactly, which is also the case for a lot of bigger deep neural networks, because the last layer is generally linear, right, where we predict the classification. Classification. So that should also be linear, at least for the last representation layer for the classification. So I think that's not a weird assumption.
I mean, like, it just says like the kind needs clinical system on top of features that was non-linear in the check.
Yeah, exactly.
So
Yeah, no, that's.
so then the state in the system of I on embedding.
Mhm. Well, I will say that it's a little bit more than that, because this HIPPO stuff is like extremely, that's like a hard derivation. I think that's not just like, it's not as simple as just applying it that way, but curious. Yeah, it's interesting, but it's very, even the way they talk about it here, right? It's like A corresponds to a uniform measure, which means that it weights every single previous concept the same. Then for a fixed DT equation, simply memorize the input and sliding windows of 1/delta T elements, and you extract. So this is what I said earlier. This is how they think about it. Like,
Right, just like,
oh, I know.
you could have distance of R2s.
Or just the 1 over, like a mean, it's just.
Yeah.
I don't think it's a specific level of possible or like class.
Yeah.
Standard linear, you know, process.
Yeah, but I think the non-standard part is the most interesting thing to the HIPPO.
It means the formal ones.
Yeah, the way they like prove that you can remember everything. From previous concept. But so
How do they actually prove that? What do they-
well, I mean, if
I
you
think
can
it's
prove
also standard approximation theory.
I think it's a form of layer, like, for example, invisible layer on the box, you have some form.
But I think it's in that paper with the pink people there.
this is it, but it's a very, I mean, if you want me to do that, here's another thing, this is like.
No, we don't have
Paragraph. I mean, we can talk about it, but they're just gonna do it.
What do they mean by remember everything?
Well, so what they, like I said before, they essentially try to find a polynomial using a projection into a lower dimensional space. And that polynomial is all previous concepts, right?
And everything is you, right? The input. They're remembering input. Or repeating the input. Repeating every time.
And they're doing that with the polynomial. And you can do that. So this is also what we said, right? LMU, for example, is when you do it with the Fourier transform. Like this projection into this lower dimensional space, you can also do that as a Fourier transform. They just choose to do it as a polynomial approximation. But yeah, they think of B and C as like these learnable filters, right? That, like what I was saying to you, Sergey, it's like, so if you have something that happened previously, you're trying to extract the important parts with this C and the B matrix. That's essentially what they're saying. But equation 2 extracts features from this window that you remember. And so C is like a way to like, okay, well, this is where we remember everything. Yeah, no way, yeah, or like just a convolutional filter.
Seems like other people compared to simple like connection because basically what I see is that X state is just kind of in like this is near transforms the kind of accumulating just
Well, X are those fundamental conditions.
basically don't increase the representation.
But it's way better than. Also, they compare.
No, I'm just saying that simple case will be residual, but like the other thing you probably can do like near one increase the representation. Instead of like creating the stuff, and you can see that it's very difficult to kind of compute.
Well, but it's not, that's not really good either.
Yeah, but LSP.
Yeah,
The same, I think the nothing is how the A matrix do. And the only intuition I have for it being useful is based on the proof of advantage gradients in LSPM. You can do this with a learnable matrix instead of A.
Yeah.
You can do it with residual connections, any kind of gate that's learnable, but it probably is going to suck. It's not going to be able to remember.
I understand. My point is just I want to say that the way how state works, it's like basically in VNet when you have skip connection, you take a feature from high resolution and passing them through skip connection. So you kind of every time step, you're not just kind of remembering with some like 18, but you passing the same kind of information from the input and such.
Yeah,
So you can kind of use the side of it, the text image and puts in nano and both.
But can I get to the point? Because I actually not even close to the actual.
Yeah, we need the complete.
Because let me, yeah, because the thing that they show in this paper actually is not even like this whole, like the HIPPO thing is a previous paper, right? The point here is that if you want to do the HIPPO paper, you have to do O n squared L operations and you have O n L space, which is huge, right? That's like insane. Like if anything
In the original HIPPO paper, they do it sequentially.
yeah, you have to multiply each time with A.
And these guys do it parallel.
Well, they're gonna go even like they're gonna go deep, and so I'm just gonna go through this pretty quickly because it's gonna get like this is pretty hairy.
No more interruptions. Yeah.
Yeah. So what they show is that you can actually write this AX with BU also with the conjugation equivalence relationship where V is a unitary matrix, where V is a matrix that is just a change of basis for like X to X tilde. And what they say is, okay, well, it would be really, really great if V was a unitary matrix because then the amount of operations you have to do is super low for the matrix multiplication, right? If you can diagonalize A, because you have to multiply by A, so if we have a fully dense matrix, we would have to do a lot of computations like n squared. But if we can do a diagonalized matrix A, then we only have to do like n, it's linear, right? And so that would be super nice.
It just means that we have to fill off subspace.
No, there is not even pro.
No, you say it's the context will be needed, like uses. So if you use
Yeah, sure. To diagonalize A, that's the hard part. So they say, so this is what I just said, but they're saying like, okay, if we can diagonalize A, then it's just a von Neumann product, which we can compute as O n plus L, which is way, way faster, right, than n squared L. So, but the issue is the HIPPO matrix, or the first issue is that if you diagonalize the HIPPO matrix, that it has huge numerical issues because you get values of 2 to the power 4i, and magnitudes of 2 to the power 4n over 3, which just any computer is going to be like super big issues for numerical issues. So how do we avoid that? Well, this is what I just said. It would be super nice if you had normal matrices or like unitary matrices, because then if we do it, we don't have numerical issues. However, a HIPPO matrix is not a normal matrix. So we need to find a way to like to still use normal matrices without compromising the fact that we have the same form as the HIPPO matrix. So the way they do this is they decompose it into a normal and a low rank matrix. And I don't know if I put this in the presentation, but the HIPPO matrix, they have multiple different versions of it. It is generally a 1 rank or 2 rank update that you can add to it. So it's super, super efficient. So now what we could do is we can decompose A into unitary matrix V, and this, yeah, it's a little, but you know, this is very fast to compute. And oh yeah, you're going to say like the lag T all satisfy rank 1 or rank 2. And so normally you'll just have a rank 1 update. So PQ. So the way you can think of it is like a unitary matrix is the matrix like Euclidean matrix, like a basis matrix. For example, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 1 would be like a unitary matrix. So that's very like a like a diagonal matrix with 1 is a unitary matrix. And PQ is what you add to it to get the Hippo matrix. That's what you do. Yeah, I'm not going to go over this because this is like crazy. But so this is the way they actually like compute this K like after they do this whole decomposition. And some of these things like black box Cauchy kernels are, I have also not gotten in my numerical algebra courses. I don't know. That's like pretty crazy, but I think what they do, yeah, no, it does work on Krylov subspaces, but I do know that. But it's essentially what they're doing is they're working on the weights of the Fourier transform or the FFT, and then they do some terms of like they do the Woodbury identity, whatever on it, and then they do the inverse Fourier transform. I don't think this is very, you don't need to like understand this at all. It just, they're just saying we can compute K with this diagonalization, in this specific way. But the most important thing to remember is just like if we diagonalize A, we're good. And then how you do that? That's this. I'll just go over like the results though. I think that's the most important part. Also, I think it's funny because it's an archive paper. So they actually said in a previous version of the archive paper, the eigenvalues were like not perfect. And so they even improved specifically a little bit the eigenvalues by doing this type of update. Okay, results. So if this is the efficiency, so LSSL is also their method, and then you S4, but they first show that it's much better than the LSSL. So it's like 30 times faster. It's 392 times more efficient in memory allocation. It is faster than linear transform. It's almost as fast as linear transformers, and with large lengths. That's table 3. And then here are the long range arena results. So these methods all couldn't actually like solve this this task, this path X, which is 16,000 sequence task, and they're the only ones that have been able to solve it now from all methods ever. And you can see how much better it does than most of these like models. They're like good models, right? Reformer has a memory, I think. They're not just like, they're not comparing it to like some random baseline. They're comparing it to like actually really good models. And the improvement is insane. Like, just look at this. At the highest is 37, they go to 59. It's almost double. And then from like 64 to 86, right? Like, it's not just, they're not just like a little bit better. They're definitely better. So that's pretty crazy to me. Yeah, I'm not going to go over this, but you can actually like look at this K matrix.
Yeah, let us stop here and move to the next.
Well, one last thing is they're also better at modeling. They're also better at classification than ResNets, and are almost as good. And they're actually better at forecasting, and they're also better than for like modeling language. I think. What they show. All right.
Yeah, thanks, Eloy. Yeah, that's basically.
I don't like